This PowerPoint is over impulse and momentum. Well, an impulse itself in physics is it causes a change in motion for a given mass. So an impulse depends on how much net force is being applied and how long that force is being applied to the mass, and it causes a change in motion. So the impulse is going to be equal to net force times time. The units is going to be Newton seconds, and there's really nothing to simplify that any more than just Newton seconds. The letter, actually, the variable we use for impulse is the letter, capital letter J. All right, so a couple examples. We've got a baseball that's thrown with a force of 800 newtons for 0.4 seconds. What's the impulse? Well, if the net force is 800 and you multiply that by 0.4, you get a total of 320 newton seconds. The next one, a hockey player makes a slap shot exerting a force of 30 newtons on a hockey puck for 0.16 seconds. What's the impulse given to the puck? And you multiply that 30 times 0.16, and that gives you a total of 4.8 newton seconds. So that's the impulse given to the hockey puck. Another way to find an impulse is actually take a force versus time graph and to be able to determine the impulse based on the area under the curve. So if we look at the graph to the right, we have an impulse over a given time period, and you can see here that we have a force of 3 newtons that's applied for 2 seconds, from 1 to 3 seconds. So that area right there will actually give us the impulse, because if you think of impulse, it's net force times time. So that's 3 newtons times 2 seconds, which gives it a total of 6 newton seconds. All right, so that's how we find impulse. We basically take the area under this graph right here, net force times time. Now, if we don't have a force that's constant, then we can still take the area under a force versus time graph to find an impulse. So we got a couple of examples right here. From 0 to 3 seconds, 0 to 5 seconds, 2 to 5 seconds, 2 to 4 seconds, 1 to 3. And these are several examples that we do in class I give to each group. These are the answers for that, for each one of those if you want to give those a try. So we're going to run through an example from 2 to 5 seconds. You can see at 2 seconds it's at 2 newtons, and at 5 seconds it's at 4 newtons. So it's not a constant force the entire time. So we're going to have to take the area under the curve in order to determine the impulse. All right, so we're going to divide this into shapes that we know. We got a triangle, a rectangle, and a square. So the triangle is going to be one half base times height. The base goes from 2 to 4 seconds, and the height goes from 2 to 4 newtons. So 1 half of 2 times 2 gives me 2 newton seconds. And then the square right here, we got base times height. The base goes from 2 to 4, and then the height goes from 0 to 2, and so that multiplies together to give us 4 newton seconds. And then the rectangle itself, the base is 1 second, and the height is 4 newtons, so that's going to be 4 newton seconds also. You add those together, you get the 2 plus the 4 plus the 4, and that gives us a total of 10 newton seconds. So the total impulse for this part is going to be 10 newton seconds. So let's say we're pushing on a table, and I add more and more force until for the first second, then I get to pushing as hard as I can for 1 second at a constant force, and then somebody comes and helps me to push for another second, and then we get to push into a max force for 1 second, and then we begin to decrease the amount of force on the table. What does the total impulse look like? So we're dealing with this graph right here. I push on it with a certain amount of force up to 200 newtons, then I push on it as much as I can for that time, and then somebody helps me push it for 300 newtons, then we push as much as we can, then we decrease the amount of force. So how do I determine the amount of impulse here? Well, again, we're going to divide this into shapes that we know, triangles, rectangles, and squares, in order to determine the impulse. So for the first one, the base is 1, the height is 200, half of that's going to be 100 newton seconds, and then 1 times 200, that's going to give me this rectangle is 200, this rectangle here again is 200, this right here, the base is 1 second, the height goes from 200 to 300, so that's 100 newton seconds, and then half of that is going to be 50 newton seconds, and then the base times height here gives me 300, and then the base times height here is going to give me 300, and then we take half of that because it's a triangle, and that we get 150 newton seconds. Add all those together, and you get a total of 1,000 newton seconds. So the total number, or total amount of impulse for this part is going to be 1,000 newton seconds. Now keep in mind that if we start with 0 force, we increase the force, and then we come back down to 0, that doesn't mean we're going to start and end at the same velocity. Because realize we have a positive force the entire time on here, which means we're going to be accelerating the entire time in the positive direction. So just because I start and end at 0 newtons, that does not mean that I'm going to start and end at the same velocity. I'm actually going to end faster than when I started. All right, now we're going to talk about momentum. So momentum is the product of an object's mass and velocity. Mass is a scalar, velocity is a vector. Whenever you multiply a scalar and a vector, you always get a vector. So momentum itself is going to be a vector also, which means whatever direction the velocity is, the momentum is going to be that direction as well. Since the velocity has a direction, momentum has a direction, thus it's a vector. So let's say we have a 2,500 kilogram car moving at 30 meters per second north. What's the momentum? Momentum is going to be mass times velocity, so we get 75,000 kilograms meters per second. And again, because the velocity is north, then the momentum is going to be north also. Notice the units here, it's just mass times velocity, so kilograms times meters per second, and that's all it is. There's no simplification of those units either.
So our next example says, what is the momentum of your book with a mass of 1.5 kilograms sitting on your table? All right, now since it doesn't have a velocity at all, then mass times velocity, which is momentum, is going to be equal to 0. So anything that doesn't have a velocity is going to have 0 momentum. All right, so what's the momentum of a 3.5 kilogram rock at the bottom of a 30-meter cliff after being dropped from the top? All right, so the first thing we need to know is how fast it's going right before it hits the bottom. So we're not talking about when it actually does hit the bottom of the cliff. We're actually talking about right before it hits the bottom, because after it hits the bottom, it's going to stop and it's going to be 0. But the point is, right before it hits, it's going to have a velocity. So we need to figure that out using conservation of energy, which we used in the last unit. We got gravitational potential energy at the beginning because it starts from a height of 30 meters and then it's dropped, which means the initial velocity is 0. When it gets to the bottom, which the final gravitational potential is going to be 0, then it's all kinetic energy. So we go ahead and use our equations. Mass times gravity times the initial height is going to be equal to 1/2 times mass times the final velocity squared. Plug in your numbers, and you get 1,029 on the left-hand side, and half of 3.5, which is 1.75, on the right-hand side, times the final velocity squared. Then we divide both sides by 1.75. That gives us 588. Square root that, you get 24.2 meters per second. Okay, so that gives us our velocity, 24.2 meters per second. That's technically downward because it's falling. 24.2 meters per second is our velocity. Our mass is 3.5 kilograms, so we multiply those together and we get that our momentum is going to be 84.9 kilograms meters per second downward. Next question says, can a bullet have the same momentum as a truck? Now, the fact of the matter that you have a bullet with a very small mass and a truck with a very large mass, a lot of people would say, well, no, they can't possibly, because they don't have the same mass. They don't have it even close to the same mass. But the fact of the matter is, you can actually have the same momentum for a bullet as you can for a truck. It's just that the bullet with a small mass would need to have a higher velocity in order to have the same momentum as a massive truck for it to have a low velocity. And another way of thinking about it is, well, if the bullet has 0 velocity and the truck has 0 velocity, both of them will have the same momentum, because any mass times 0 is still going to be 0. Now, the confusion here is not really momentum. What a lot of people are thinking of is actually inertia. Now, can the bullet have the same inertia as a truck? Well, no, it can't, because inertia has to do with the mass. So the amount of mass the object has deals with the inertia, but mass times velocity deals with the momentum.
So now we're going to talk about change of momentum. Really, momentum is not a big deal unless you talk about the change of momentum. So we're going to talk about how to find change of momentum and then why that is later. By the way, I don't know if I mentioned that momentum is, we use a P to designate momentum. So a change of momentum, just like changing anything, is final momentum minus the initial momentum. So we find the final momentum, subtract the initial momentum, and that gives us our total change. So this example right here, we have a 2,500 kilogram car moving at 30 meters per second north, and then it slows to 10 meters per second north. What's the change of momentum? Well, the final momentum is going to be 2,500 times 10, and the initial momentum is 2,500 times 30. So that gives us 25,000 as the initial, and then 75,000 is 25,000 is the final, 75,000 is the initial. Final minus initial is going to be equal to negative 50,000 kilograms meters per second.
So in this next example, it says find the change in momentum of a 0.25 kilogram ball initially rolling with a velocity of negative 3.0 meters per second and accelerates and is now rolling with a velocity of positive 3.0 meters per second. Now, something to keep in mind here is that the direction actually matters when it comes to velocity. So the fact that we have a negative 3 meters per second here and a positive 3 meters per second does make a difference in the equation. So we have our equation for change momentum. Change momentum equals mass times final velocity. So mass, the mass is 0.25 times the final velocity, which is 3.0. That gives us 0.75 minus mass times initial velocity. Mass was 0.25 times negative 3, and that gives us a negative 0.75. So we got final minus initial, so that's 0.75 minus a negative 0.75, and we get a total of 1.5 kilograms meters per second.